Hello everyone. The other day at work, I had to implement a transformer model, and then I said maybe I'd talk a little bit about the training time versus the inference time in transformers, and record a video and put it out there. Maybe someone else can use it. So today for this video, I will be talking mostly about the input and output of the transformer model. I won't go into details like the embedding layer or masking or attention layer. So maybe I can talk about them in another video, but today would be very a general overview of the training versus the inference in transformers. So in the beginning, I would like to also apologize for two things at least. First, because of my handwriting, because as you can see, it's not very beautiful. But the second thing is also I'm going to use an example for English to a Spanish translation, and I'm not a native speaker in any of these languages. So I would like to apologize for any mispronunciation. Okay, let's get to the work. Let me draw a box here. And so as you know, probably the transformers have one encoder and one decoder. So let's say, this is our encoder layer, block. And then we have another block which is called decoder. And a lot of layers goes into these blocks, but I won't be talking about them. Okay, so let's say we have a sentence as I am very happy, and we would like to translate it to the Spanish sentence, estoy muy feliz. Okay, first thing we do is usually we tokenize our sentences. So for example, let me change my so for example, I could be one token, am could be another token, very could be another token, and happy would be another token. There are different ways of tokenizing sequences, especially for text. Like you could go for subwords, for example, tokenization. So that would be like, for example, HAP could be one token and PY could be another token. But just for simplicity, let's go with the word level tokenization for this example. So what we want is to be able to basically pass this English sentence and then get the Spanish sentence out from the network. So we want to, for example, pass this token, this token, this token, and this token to the network, and then to be able to recover this token, and this token. Okay, so but when we want to basically pass the tokens to the encoder, we cannot pass the word to the model. We need to convert them to some numbers and then pass those numbers to the model. So what we do here is basically, let me change my color again. These are called tokens, and then we go for we convert them to token IDs. For example, the first token I gets an ID of, for example, 2, and then the second token maybe get 31, this gets to 55, and then happy may get to 128. And these are called, let me change the color again, these are called token IDs. So we convert them to token IDs and then we pass them to the network. Like, for example, this goes to the network, this goes to the network, and this as well, and all of them. Okay, and then what the encoder does is basically outputting some vectors for each of these token IDs. Like, for example, for the token ID 2, it may generate a vector such as 3.1, 2.6, and then dot dot dot. So the number of elements in that vector depends on the model dimensions and everything. So I won't be talking about those again. But this is basically what the encoder does. And then for each of the tokens, it will generate a vector. So it goes for the 31, etc., and then keeps going. Okay, so this is what the encoder does, and for training, this is how we pass the tokens and token IDs to the encoder. Okay, before we get to the decoder, let me change these and make them a little bit smaller because we need them for something. So that would be, the first one would be estoy, muy feliz. Okay, so what we are going to train the network for is basically, given the English sentence I am very happy and a series of tokens, let's say in Spanish, predict for me the next token that comes after the last Spanish word. Like for example, I'm giving you I am very happy, and then I give you a start token because at first I don't have any tokens to give you, and then you go through the network. Let me go through the network and then predict for me the first Spanish words that should come after the start token, and hopefully the network can predict for us estoy. And then I do this for the rest of the tokens as well. For example, another thing would be I pass you the English sentence I am very happy and the start token and the word, Spanish word estoy, here to the network, and then you go through the network and please predict for me the next Spanish word that comes after estoy. For example, hopefully this time you can give me muy. And then I do the same for the other token. Like I say, okay, this time I pass you I am very happy, the start token, and the estoy, and also the word muy this time. And then go through the network and please predict for me the next token that comes after muy. That could be hopefully feliz. And then at the end, I pass you again I am very happy, the sequence, a special token start, estoy, muy, and this time feliz. And go through the network and predict for me. This time I want you to predict for me, let me write it down with a different color, an end token. That means that the sentence is finished. So hopefully this time you can give me the end token. So I hope the message is clear. We are passing an English sentence, a sequence of words to the network, and a sequence of Spanish words or tokens to the network, and we are asking the network to predict the next token that comes after the Spanish sequence we fed to the network. But again, note that I cannot pass the words or the tokens directly to the network. I have to convert them like what we did for the encoder to token IDs and then pass those IDs to the network. So let's say the start token maps to ID number 3, and then estoy maps to 54, for example, and then muy pass is mapped to, for example, 67, and the last one is mapped to 256. And then after that, I can basically pass those token IDs to the network to be able to train the network. So I guess again, write down token IDs. But again, when the network is being trained, it's not going to output exactly the word estoy or muy or feliz. it's going to output some vector again. And I talk about this vector in a little bit. But this vector could be a very huge vector. And for example, let's say it could be 50,000, 30,000, or more or less. Okay, let me actually erase this and yeah, write it down here smaller maybe. Yeah, so for each of these token IDs, the decoder outputs a vector, a giant vector, and that which is like basically consists of real valued numbers, like for example minus 2.3, 7, and dot dot dot. So these are called logits. But let's talk about this vector here to understand it a little bit deeper, because we are going to basically find out our words here, stoi, moi, feliz, from these vectors here. And as I said, the network produces one vector for each. But again, this giant vector here over here is converted to another vector. It's not actually converted, it's actually normalized, because it has real values. We want to normalize them into probabilities. So it's normalized using like something like softmax function to a probability, like for example 1 second, 1/4, and then the list goes on. And then this will be done for every vector. And now I can talk about this giant vector here again. So 1 second, 1/4, and the list goes on. But again, before talking about that, I would like to bring your attention to what we said earlier. Here we had tokens and then token IDs. So when we are pre-processing our data, basically we need to map each token, as I said, to a token ID, and that will give us a dictionary of, for example, tokens to IDs. Like for example, the special token S is mapped to 3, and then stoi is mapped to 54, and then the list goes on. And then the size of this dictionary, let's say call it dict. The size of this dictionary would be your vocab size, basically. And then we will create a reverse of this mapping as well, which is called, let me also change the color, which will be the reverse of this. So it would be IDs to token dict or mapping, whatever you want to call it. And then that would be exactly the reverse of this. That would be like number 3 is mapped to token start. And then 54 is mapped to token stoi. And then the list goes on. And finally, the number of elements in this giant vector here would be the same as this dictionary over here. So they map together. But let me change this to 112, 114, and then remove this, and then goes, and then 1 second, and then goes. Okay. So this vector here, the elements are mapped exactly to the token IDs. For example, this could be ID number 0. Let me change the color again. Number 0 maps to this number. ID number 1 maps to this. And then somewhere along the line, like for example, let's say ID number 54 maps to this, and then the list goes on. Then among all these elements here, we pick the highest. Let's say this ID number 54, which has a value of 1 over 1 over 2 has the highest value, and this is selected. Okay, and then we look at our dictionary. We say, okay, the ID number 54 was selected, and ID number 54 is mapped to stoy. And then we go and output stoy. But in training, we don't need to output the word itself because we use a cross entropy function for loss. And then for that, we only need this 54, the ID 54. And then in our labels, we look at our dictionary over here. We see, okay, the stoy ID was 54. And we also predicted 54, then the loss for that token would be 0. But let's say, for example, for Moi, the real token ID was 67, basically. So this was 67. And let's say after we do everything, we get ID of 64. And then there would be a loss here, and then we calculate the loss and then propagate it backward. Before we move on to the inference, I want to talk about a few points actually. So if you look at the original paper, in their model picture, they have a text says in the decoder part that says it's shifted by 1 or shifted right. So what they are talking about is exactly this. Like if you remember the output of the network, let me change the color again. The output of the network, we are expecting this sequence, but then for the decoder input, we are passing this sequence. And if you see, these two sequences basically are the same, but only shifted by 1. Basically, the decoder input is shifted by 1 to the right of the version of the decoder output. And then the next point is that when I was trying to explain the concept itself, I basically try to tell you the sequence that the past is basically is tokens are passed or 1 by 1. But during training, we don't need to do that. Basically, what we do is just we shift the labels here, the output, by 1, and then pass the whole sequence to the network. But then what the network is going to do is basically for this one here, it goes all the way and output, like for example for Moi, the fleas. But it will only use the tokens, star token, stoy, and Moi, and it will mask the fleas and it won't see the fleas. Okay, another point is about the padding basically, because when we are training our model, we are going to pass multiple of these sentences and then put them in a batch and then pass them to the network. For that, they need to be the same size. But for example, you have I am very happy, but then the cat is not happy, for example, right? These two sentences, I am very happy and the cat is not happy, they are not the same length, right? So what we do here in that case, we pad, actually we generate a token called padding token basically, and we put it into these dictionaries here, and then we append that padding token to the shorter token. So for example, we consider the longest sequence in our training set, and then we make every other sequence which is shorter than that the same length, with just appending some padding tokens at the end of them. But then this padding token also gets its own ID, let's say 72, and then it goes through the network again, and then the same goes. So for the English sentences, we do that, and we do the same for the Spanish sentences as well, because they may have actually different lengths. So we append the padding token, for example, for this one, and then maybe another sentence needs to be padded with 2, and then the next sentence, something like that. And then this token again goes through the same process, 341, and then goes through and finally, in our output labels, we also consider padding them because they are not the same size, right? But this time we can pad them, for example, with actually some numbers, but for cross entropy function that we use for the loss function, we can, like in PyTorch, for example, it has a option which is like ignore index. So basically we can pad them, for example, with -100. This is the default value for PyTorch cross entropy function. And then if we pad them, for example, we had one padding here and we pad them with -100, the PyTorch cross entropy function, when calculating the loss, will just ignore this index over here. So it won't be considered for loss and everything. So basically, when training our network, we are going to ignore the padding tokens and their contribution to the output. So, and then you can just pad as many as tokens you have here, -100. But this shouldn't be exactly -100. You can change this option in PyTorch and you can pad with any number you want, but hopefully not the numbers that is one of your token IDs. Okay, so this was the training for transformer models, like including both encoder and decoder blocks. Now we can go to the inference for the network. Let's go here and write down inference. We will have the actually same structure here, encoder and then decoder, right dec or right end here, and then the same thing goes here, then goes here, and then we have the inputs to the decoder and then the output. Okay, before that, let's remember that what the network has learned so far. The network has learned, for example, given an English sentence, a sequence of tokens to output the next token that comes after the sequence in the decoder. Let's say we have an English sentence, I eat pizza here, and we want to convert it to Spanish, and I think that would be hopefully yo como pizza. But then we don't want to pass, we are not in the training mode, so we don't pass that to the network, but this is just what we want. And so let me just get rid of it, and then during the inference, we pass the network in the first timestamp, right? Let's say first timestamp. We pass the network I eat pizza and the start token, and we ask the network to predict for us the first token. And hopefully that was yo como pizza. And hopefully when the network is trained properly, and the thing that it will produce here would be yo in the first timestamp. Then also remember that we need to, let me change the color, we need to pad this with our padding tokens. And then when we are getting the output, we will just look at the first one here and we will ignore this over here, whatever is out. And then in the second timestamp, let's go down. Okay, so that would be the encoder, decoder, the whole thing. We actually don't need to pass I eat pizza again. We can cache it, but let's say for simplicity, we pass it again. But this time we pass this to the network. We pass the start token, and then the first token that the network generated here, that was yo in the first timestamp. This is the second timestamp. So the first one, in the first timestamp, the network generated yo. So we get that one and then we pass it here, yo, and then we pad again. And then we pass everything to the network. And then this time, when the network outputs something, let me change the color. remember, the network has learned to see the I eat pizza and the start token and you, and then produce the next expected token. That would be, for example, hopefully Como. So in the second timestamp, what we do here again, when we get our predictions here, the first one we already saw, the yo, so we don't need that one. But this time we go to the yo and then we see what would be the output for that one. That would be como, and we take that one as our prediction and we ignore the rest. So far the network has predicted yo and como. And then for the first time step, the prediction was only yo. And then we go to the next time step again. So let's go, okay. That would be the third time step. But then here would be the encoder, then the decoder, and then these arrows here, 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 here. What we do here is this. And this time, like so far, the network has predicted yo and como. So what we do here is we shifted by one, we prepend the start token, and then yo, and then como, and then we pad them again until the required length. And then this time the network will still predict yo here, como here, and hopefully this time the network predicts pizza here. And then again for the next predictions we just ignored, and this time we pick pizza. So the prediction for the network in third time step would be yo, como, pizza. And then we continue this for the next time steps, and hopefully at some point the network produces the end token, and then we finish our prediction. So that is basically a high-level overview of the inference in transformers. But remember, in inference time, we are going through multiple timestamps. So we are changing our input to the decoder every time and then getting a new prediction every time. Like for example, here we went through 3 timestamps, the second timestamp here and the first timestamp here, and we are changing, as you can see, the input to the decoder here. This is decoder and this is encoder, and also here as well we are changing the input. But then we are also, if you think about it, we are also taking only the last prediction here. Here that would be pizza, here that would be como, and here would be yo. So the inference, and during the inference basically we go through multiple timestamps, but if you remember during the training that was only in one go. So basically one timestamp we passed this sequence, I am very happy, and then the sequence shifted by one, start token estoy muy feliz, and then the labels would be estoy muy feliz and the end token. Okay, before I finish, I would like to also talk about something else, a little bit of implementation details. If you remember, I talked about during training when we make a prediction, we compare the label 67, for example, with like token ID 67, with the predicted output from the network, which is like 64. For calculating the loss using, for example, in PyTorch cross entropy function, we pass this, let me change the color, please. We pass this, for example, token ID, the true token ID that should the network output 54. But the next thing that we pass for comparison is not the probability vector, and it's not the output token ID. Let's say here it produced 54. We will pass it the logits. Actually, this is what the network produces. So basically for comparison during training, we only use 54 and these logits here, the output by the network. And then we do the same for other tokens as well. We see, okay, the true label for Moi, the token ID was 67, and then the output by the network was this network, but was this logit vector. And then we pass that to the cross entropy function of PyTorch. And then we do the same for everything else. Like for example, fleas, the true label was 256. 256, and then let's say for n token it was the true label was, for example, I don't know, 451. And then we do the same for everything else. Like for example, for this one we go for 256 and then the outputted logits here. And then we do the same, and then at the end same again for 451, and then the outputted logits here, and then we append our actually 100 minus 100s here, and then the rest. And then for these also we will get some output vectors, and then we pass them, but it will be ignored by the cross entropy function because of these minus 100s here. So I just said about like 67 and then 64 because it was easier conceptually to understand what the network is actually doing and then how it's being trained. So in this video I didn't go through many details such as embedding layers, masking, attention layer. Those are details inside these boxes, encoder and then decoder. If you find this video useful, please let me know. I can always make a video for those as well. But I hope you enjoyed this video. In this video actually we talked about input to the encoder and then input to the decoder and the output of the decoder during training and inference. Very high level overview. I hope you enjoyed this video, and thank you very much for your attention.